Okay, so in order to apply the system identification for a given measured data in terms of the position and the time, and so we need to give the mass spring damper system in here. We need to build it. But as I said, this is not required for your applications, guys. Okay, because you have already data set for a given the t and the x position, and so the m is assigned to the 1. It's 1 kilogram, and also we need to give the true system parameters in here. K true is equals to the 20, and C true is equals to the 2. Okay, and after that the natural frequency and damping ratio can be defined with what the omega, and true is assigned with what the sqrt k true value divided by m. Okay, and zeta true value is assigned c true divided by 2 times m times omega and true. Okay, and after that we need to define the time vector just like this one. The time vector is the t, it's the line space 0 to 5 and 5 times 100 points. 100 is the sampling rate, and so we have the 500 points at 5 seconds, which means that we have the 10 millisecond sampling period. Okay, so this true can be defined in the transfer function domain just like this one, omega n true square form, and this is the characteristic equation 1 2 times zeta true times omega n true and omega n true square. Okay, these are the transfer function, and after that for a given step function y true value and t out value is obtained with the with the step sys true with the with the t values. Okay, these are basic response of the of the R systems. Okay, and so if I run this code, and then we will have to the to R step response just like this one. Okay, this is our measured data, but in the measured data there always be a noise. Okay, so in order to add the noise level is equal to 0.02, and noise level or the noise values, the noise level times round n size of y true. Okay, this is the random Gaussian noise for this one, and y noisy is defined with the the y true plus this noise. Okay, this is noisy data, and so if you measure any system response from the mass spring damper to any other second order system, you will have this y noisy signal. This is the emulation of this measurement parameters in here. Okay, after that we need to apply the R steps, the identification process. Okay, first of all we need to apply the filtering, right? And so we need to take the order of the filter, Butterworth filter in here, Butterworth filter just like this one, and so the cutoff frequency is assigned, for example, the 5. You can set the different values in here. Okay, and fs can be assigned with 1 divided by t2 minus t1. This is the sampling period, and so 1 divided by sampling period gives us the cutoff frequencies, and so Wn is assigned to the the cutoff frequency divided by to the fs divided by 2. because the sampling rate is, for example, 100, and so we can only filter to the what up to the 50 hertz. Otherwise, the higher values of this frequency cannot be seen at this sampling rate. Okay, this is the normalized frequency, guys. So, in order to design Butterworth filter, we need to build the B and A style. Numerator and denominator of this part, and so butter function can be used with the order of these terms and these normalized frequencies. Okay, and so apply this filter on noisy data, just like this one. Y filtered is equals to what the field is another function to apply the B and A and Y noisy signal. Okay, this is another method that's provided from the Matlab programs, and so we can draw these signals in here. The figure is the plot T out and Y noisy signal, the B and line white 1. Okay, and hold on should be put in here, and we can copy of these terms. Y filtered is assigned to green 1.5, and also can recopy of these terms. The Y true is the true dynamics, and this is assigned R dot. This is what? Okay, X label is the time sec. Y label is the displacement meter. Okay, and the legend is assigned with the, in the first place, noise data is given in here, and filtered data is given in here, and true response is given in here, and also we need to move with the put the grid on. So we have the blue line is the measured data, and the true response is that red line. Okay, but the filtered data mostly removes the unwanted signals in here, and so we can model based on this filtered data to the true response. But how we can do that? And so in here, in the step estimating time parameters. Okay, just remember that in the first place find steady state value. Okay, the steady state is equals to the y filtered at the end of this point to the end. Okay, because it returns to the steady state values, and so find peak value and its time. It's related to the t peak and the overshoot values. Okay, and so peak val and peak idx is assigned with the max function y filtered. Okay, this returns to the peak values, and it's related to the time parameter, and so tps is assigned with the t out with the index of the peak index. Okay, idx. So after that we need to calculate the percentage overshoot values with respect to the steady state values, and PO S is equals to what? Peak val steady state divided by steady state times 100. Okay, and so after that estimate the damping ratio in here. Zeta estimation is equalized with the minus log PO divided by 100 in here. After that the SQRT function is given in here with the values of the pi over 2 plus log PO divided by 100. Okay, and so this should be multiplied with the with these terms. Okay, Just see that S square T and I'm sorry. Okay. This is the basic formula for estimating the zeta approximation. And after that, estimate the natural frequency values in here. Omega n est is equals to the what? Pi divided by, this is the peak time formula, P est multiple times SQRT minus zeta est square. Okay. So how we can find to do what? The stiffness and damper coefficient. K est from the formula m times omega n estimation square. Okay. And C est is equals to 2 times m times zeta est times omega n est. Okay. This is the values of the K and C, but the estimation values. Okay. And so in the first place we need to printf estimated parameters from filtered data. Okay. So the fprintf damping ratio or zeta values percentage dot for fn. Okay. And zeta est. This is the first values. And in the second one we need to write the natural frequency. Okay. And so wn in here or omega n. So this is replaced with what? The omega n est. Okay. And also we need to write the stiffness values. The K, this is equals to what? The K est, and this is the what? Damper coefficient, C. Okay. This is estimated parameters. And also we need to write the what? True parameters in here for the estimation process. And so true parameters from filtered data, not filtered data. We have all it right now. And so this is zeta true, this is omega n true, this is K true, and this is C true. Okay. So if I run this code and then I'm sorry that the PO does not in here, we have error at the new line Q. I'm sorry, POS. Okay. And so if I rerun this code and then we will have the damping ratio in here 0.24 and the true parameters is equal to 0.22 is closing. Natural frequency 4 times 49 estimated values, but the natural frequency is in the true parameters 4.47. This is good. And so stiffness, estimated stiffness 20.18 and the normal stiffness is 20. It's good. The damper coefficient is 2.21, but the true damper coefficient 2.0, right? So this is important. So this is a good result for the what? For the second order system. We are closing to the what? The true parameters and the estimated parameters based on these informations. And after that, how we can compare these results? Plot estimated step response in here. Cis est is equals to the what? The TF omega n est over square 1 2 zeta est times omega n est and omega n est square. Okay, and so y estimation is obtained in here, and so we don't need to define the t values because we have it already. Cis est for a given t values. Okay, and so we have two response, estimated step response and the true step response in here, and so we can compare the figures in here. The plot t out can be drawn in here, y true values, and this is assigned to the green, and line white is assigned without 1.5, and hold on should be given in here, and plot t out and y estimation values and k dot values, and the line white with the what 1.5. okay, and so the x label time sec and y label displacement meter. And so the legend values is the, first of all, this is the real data, and the second line is the estimated response. Okay, and grid on must be open. And so if I put and estimate the step response, and then the real data is the what, the green line, but the other terms is the what, the dot black line is the R system response in here. Okay, and so it's closing to each other in here. That's a good result for the second order system characteristics. And so if I rerun this code, and then we will have the same results. But for example, if I choose the different values of these terms, for example, this is equals to 10, for example, just see that we model this term either, or we can assign the C true value is equals to what, a 3, and so we can also model these terms just like this one. See, this is an automated algorithm for the what, for the system identification of the mass spring damper system for an unknown C and K parameters. You can easily use these techniques in the what, in the real-time applications or the measured data, on the measured data, guys. Okay, so that's all for the system identification for the first order and the second order systems.